So let's proceed into our Julia videos. Let's talk about functions. How we define functions in Julia. We define functions in Julia using the function keyword followed by anything that goes inside the function and finishing with the end keyword. Pretty much like we do with the other blocks like begin, end, if, else, for loop, and so on. So we start with the function, and then we have the function name, the arguments, and then we have the function body inside the function, and we return something, and we finish with the end. This is the standard where you define function in Julia. You also have the compact assign form. For example, here I pretty much do function name, so round number. It takes an x as argument, is just equal round x. So if I run this and I call round number with a float, it works. If I call round number with an integer, it also works. But Julian, we have specialized methods that we can define a function depending on the type of arguments the function takes. It has custom behavior at runtime. What this means is that if I can define a round number function that has a custom behavior for floats and a custom behavior for integers. And this is what I'm doing here. This is a round number for if x is a float, I pretty much say x is a type of float, then you are going to do round, you are going to call the round function into that x. And this is not a type annotation. This is not IOU like in other languages such as Python. This is way more strict. So this will will get an error if you don't have a custom method for the type you are calling. So this is much more strict than type annotations. It's not an annotation. This is a custom behavior if you call a function round numbered where you are calling into an argument x, and that argument x is a float 64. So if a float, we are going to round it up. This is the first function. Now, the second custom behavior is if it is a type of int 54, you don't need to round it. Integers are already round numbers, so you just return the x. So it's pretty much a no-op or the identity function here. And if I run this, you see that we have our round number. This is a generic function with 3 methods because we have the first method we define here at line 67. We have the second method at line 74 that we defined here. This is the specialized method where we are calling with a float. And we also have the specialized method if we call this with an integer. And you can see if you use the which macro, you see that if you call round number with a float, we get back that this is calling the round number. X, it's float 64, defined in this file here at line 74. And that's pretty much it. If we call with the round number in an integer, we get back that we are calling the other method, the method that takes integer, and this defines the same file, but now it's in line 75. And what happens if you call that? So if I do which round number of a Boolean, like true, you see that now we are using the round number, the no specialized method just with any x, and it is in the line 67. So this is the one here. And this is a very simple example of multiple dispatch. Actually, it's not multiple, it's single dispatch. If we had more arguments, we call multiple dispatch, but this is pretty close. Now let's take a look at anonymous function. So what are anonymous functions in Julia? So in Python or in R, we have something like Python, we have something like a lambda x square. And in R, you have something, it's a function, it's function x, and then x square, something like this. So this is an anonymous function in R and Python. To that, we have since it's a scientific computing language, it's much more mathy and scientific. We do have this notation here. So x, which maps to x squared. So it's pretty much what you see as a function definition in a math textbook. And I find that pretty amazing, Juliet. So this is pretty much as you would read in a math textbook. So the function that maps x to x squared. And if we do type of this, we know that it's a simple reference because that's the name, that's why it's called anonymous function. It's an anonymous function. It is a simple reference. It's not defined. We generally use the anonymous functions in a math call. So if you hover over the map, you see that maps a function to a collection C. So we are mapping this function here, x squared, to 3. So this is a single value of this gets back a 9. And we can also do that for a collection of values. So here I'm defining an interval 1 to 10. And if I do this, I get back a 10-element vector of scraps. So it grabbed all of the interval 1 to 10 and mapped the x to x squared anonymous function to every single element of 1 to 10. We can also do more values as tuples. So I can pretty much say, okay, map x and y as a tuple to this function. Take the x squared plus y. So this maps a function in the two-dimensional space. So a function that has inputs in the two-dimensional space and outputs as scalars. And of course, I need to pass in two collections here because one collection from x and another collection from y. So here, I just press in simple numbers. So 2 squared plus 1 is 5. I can also do, okay, map x squared plus y for every x element in 1 to 3 and every y element in 3 to 5. So then we get back a vector of results. So 1 square is 1 plus 3 is 4. Now we go to the second element of the list. So 2 square is 4 plus 4 is 8. And then we get back 2 square is 9 plus 5 is 14. So that's what we get back here. I can also make my anonymous function a function. And yes, that's not that obvious. So I can pretty much call this function. I can put a bracket in it and I can call this with so this becomes a function and this becomes the argument. So I can do this and it works. I can also save my anonymous function as an object and I can call that object into an argument and it also works. And an example, just to finish this video, an example of how we use the map function and the anonymous functions in Julia is, for example, suppose we want to create a population. So we want to map ID into subject ID equals ID for every ID in 1 to pad. So this would return a population. And as you can see, we have a population of PEM subjects because this created a subject for every one of those elements and then combine them into a vector. And from the population video chapter in this course, we saw that populations are pretty much collections of subjects, vector of subjects. So that's it, functions and anonymous functions and the map function in Julia. I hope you enjoy it.